differentiation rules. So we've been doing it the long way, like looking at all of those limits, using the difference quotient. Now we're going to learn all the shortcuts. Because now you know what it means.
That's so
Hurtful, not gonna lie.
You're what?
Said that was kind of hurtful. Not
No! But now you know that it's really just the slope of a line at any point. Like, we're good.
You could have just told me that.
It's not my jam. Okay, so here are the differentiation rules. Okay, so when we use that definition for derivative, it's lengthy, it can be challenging, but as we saw early on in pre-calculus, we have some rules that allow us to take some shortcuts. Okay, so here are the basics. Okay, if I have a function that's a constant, so like y equals 2, that's just a straight line, right? Well, what's the slope of a horizontal line? 0, okay? So the derivative of a constant is 0. Okay? Because it's just a horizontal line. Okay, and then the second type of function that we're going to look at is just the most basic function where you have x raised to a power. Because most of our other functions are just combinations of x raised to a power and constants. Okay, so this gives us the power rule. When we have x raised to an exponent, we have the power rule. Okay, so let's say g of x equals x squared. Well, you know from some of the things we did in the past week and from early on that the derivative is 2x. Okay? So our rule then for all x's raised to a power, so if f of x equals x to the n, f prime of x, or the derivative, is nx to the n minus 1. That's our power rule. The power rule works for negative exponents as well. So if I have f of x equals 1 over x to the 4th. Well, that is x to the negative 4. Just remember that little conversion. So following our rule, f prime of x then would be negative 4 times x to the negative 4 minus 1, which would be to the negative 5th power. And if for some reason we wanted to write that back as a fraction, that would be negative 4 over x to the 5th. Okay? So the power works for negative exponents. It also works for fractional exponents. So we also have the power rule with fractions is the same thing. If I have f of x equals the square root of x, that is x to the 1/2 power. So f prime of x, or the derivative, is 1/2 x to the 1/2 minus 1, which is -1/2. And again, if I wanted to write that as a fraction, that would be 1/2 times the square root of x. Okay? If I wanted to rationalize that, I would take it times the square root of x over the square root of x, which would give me the square root of x over 2x. So just recognizing that this, and this are all the same expression. Okay? So the power rule works for regular powers, negative powers, and fractional powers. Great. The sum rule is super easy. Oh, good. All right, the sum rule. The sum rule is simple. If you have two functions being added together, you can take the derivative of the first one and add it to the derivative of the second one. Okay, so it looks like this. If we have j of x equals f of x plus g of x, then the derivative, j prime of x, equals f prime of x plus g prime of x. Okay, so for example, if f of x equals x to the 5th plus 7. Well, x to the 5th is a function. 7 is a function, just a constant, right? So I can take the derivative of this one plus the derivative of that one. So f prime of x is 5x to the 4th plus, what's the derivative of constant? 0. Okay? So the derivative of a sum is just the sum of the derivatives. The same is true for the difference. We do call it its own rule, the difference rule. But it's the same thing. So if you have a function that is the difference of two functions, then the derivative of the function is the difference of the derivatives. So for example, if f of x is x to the 5th minus 7, then f prime of x is 5x to the 4th minus 0. Cool? Okay, then we have this constant multiple rule. Okay, so the constant multiple just says if you've got a function that is a constant times another function, so like 2x squared, then the derivative is that same constant times the derivative of the function part. So for example, if f of x equals 2x to the 5th, I just pull that 2 out. So f prime of x is going to be 2 times the derivative of the functional part, which is going to be 5x to the 4th, which gives me 10x to the 4th. So far, so good. So sometimes I have to use those rules all together. So if I had f of x equals 2x to the third minus 6x squared plus 3, and I want to know what the derivative is. What is the equation that would give me the slope of the tangent line at any point on the graph of 2x to the third minus 6x squared plus 3? So I have a difference, I have a sum, I have a constant, multiple, and I have an exponent. So I have to use all the rules together. So I'm just going to take them in order. So the derivative of this one, that's the constant, it stays out in front. This is going to be times 3x squared, because I took the exponent in the front and then decreased the exponent by 1. Now I'm going to subtract. I've got a constant, so 6. Take the exponent and bring it out front, so 2x to the 2 minus 1, which is x to the first. And the derivative of a constant is 0. So now I can simplify. So f prime of x is 6x squared minus 12x. So we just use them together. So let's say that this, well, not let's say, this equation would give me the slope of a tangent line at any point on the graph, on this graph. So what if I wanted to know okay, so this gives me the slope, right? Only the slope. If I want to find the equation for a line that's tangent to the graph at x equals 1, I have to take this slope and put it in the equation for a line. Okay, because this is only the slope of the tangent line. Okay? So I want to know what is the derivative, or what is the slope of this line at x equals 1? Because that's what it told me. So I have to find f prime of 1. Okay, so what's the slope of this line at x equals 1? Well, it's 6 times 1 squared minus 12 times 1, which is 6 minus 12, which is negative 6. So negative 6 is the slope of the tangent line. But I want the equation for the tangent line. So I'm going to use that slope with a point and find y equals mx plus b. Okay? So I've got y equals negative 6x plus b. I know that much so far. Okay? Well, I need a point on the line, right? And we want a point on this line, because that's where we're finding the tangent line. So I'm going to put f of 1. So I'm going to find f of 1, because that's going to give me the y value. So 2 times 1 to the third minus 6 times 1 squared plus 3 is 2 minus 6 plus 3, which is what? Negative 1? Okay, so my point is going to be 1, negative 1. So now I have a point, and I have the slope. I can solve for b. So I have -1 equals -6 times 1 plus b. So b equals 5. Now, the equation for a line tangent to f of x equals 2x to the cubed minus 6x squared plus 3 at x equals 1 is y equals -6x plus 5. Yeah? No. Remember we had this graph, whatever it looked like.
Oh, yeah, I just.
Okay. Okay. Oh, okay. It wasn't the concept, it was that I maybe had, okay. Legit. Okay? So that's how you would use all of those rules together to find either the derivative, and then you can use the derivative to find the slope of that tangent line at a point, and the equation for the tangent line. Okay? There are a few more rules. I think you're good. We can go on, right? Do a few more today. I think so. So the next two are just the product and the quotient rule. They're similar to each other, just like the sum and the difference rule are similar to each other. Okay? Okay, so the product rule means that we're going to have a function that's actually two functions being multiplied together. So f of x times g of x. Okay, this is where it sort of gets tricky, but if you just refer back to what you're supposed to do, you'll be fine. Okay, so the derivative is going to be the derivative of the first function times the original second function plus the original first function times the derivative of the second function. Okay, so you take these two functions, you find the derivatives of both of them individually, and then you put them in this formula. And that will give you the derivative. So let's see what that looks like. So let's say I have f of x equals x squared plus 2. There's my first function. And then I have 3x to the third minus 5x. So I have two different functions there. I have x squared plus 2, and I have 3x squared minus 5x. Okay? I could multiply that out and get one big long polynomial, and then use the sum and difference rules, if I wanted to. That would work just as well. Yes?
So f of x is like, if you look at it, it would be j of x in the
Yeah.
example. Okay.
Yeah, so this is j of x. This is f of x. This is g of x. Okay? If we're looking at our example. So let's go over here and just find our derivatives. So I'm going to say f of x equals x squared plus 2. That's my first function. So f prime of x, or the derivative, is 2x plus 0. Yeah? Okay. Then g of x is my next one, is 3x to the third minus 5. So the derivative of that one is 9x squared. So now I'm going to put them into my, form.
Minus 5x, not 5.
Oh, did I tell you 5x? Oh, okay. Oh, I did. So that's going to be minus 5, right? X to the 1, 1, 1, okay. Great. So now I can put them in my formula. So the derivative is, okay, the derivative of the first one. So 2x times just my regular old g of x. So 3x squared minus 5x plus my original f of x. Did I mess up?
3x cubed.
Thank you. Okay, so now I'm looking for just plain old f of x, which is x squared plus 2, multiplied by g prime of x, which is 9x squared minus 5. I mean, in technicality, that's the derivative, and you could leave it that way, but we do like to simplify a little bit. So the derivative is 6x to the 4th minus 10x squared, and then I'm going to FOIL this part right here, plus 9x to the 4th plus 18x squared minus 5x squared minus 10. And then I'm just going to combine like terms. And I end up with 15x to the 4th plus 3x squared minus 10. So this function right here would give me the slope of the tangent line at whatever point I wanted. The hardest part about the product rule is just keeping everything straight. And then the quotient rule, super similar. With a little twist. So this is our last one. This is the quotient rule. Well, the last one for today. Okay, so that means if you have a function that is a function divided by another function, so f of x divided by g of x. As you would expect, the derivative is going to be the derivative of the numerator, so f prime of x, times the denominator, minus the numerator times the derivative of the denominator. So just like we did with the product, except that we're subtracting, and we have to divide by g of x squared. So you're going to take that original denominator and square it, and that becomes your denominator for your derivative. Okay? So let's look at an example. If we have j of x equals 5x squared divided by 4x plus 3. So this is my f of x. This is my g of x. So I know I'm going to need the derivatives of both of those. So I might as well go over here and do them. So f of x is 5x squared. So the derivative is 10x. G of x is 4x plus 3. So the derivative is just 4. Now I can put them into my format. So I'm going to start with f prime of x, which was 10x, and multiply that times my original g of x. Then I'm going to subtract my original f of x, 5x squared, times the derivative of my g of x, which was 4. And then I divide by my original g of x squared, which was 4x plus 3 squared. So this is a fine derivative. Like you could substitute a point, you could substitute an x value in there and find a slope at that point. You can also simplify a little bit though. I sort of had to go down a rabbit hole here. This ended up being 40x squared plus 30x minus 20x squared. I just distributed the 10x and then subtracted 20x squared. Divided by 4x plus 3 squared. And then I combined these like terms, so 40x squared minus 20x squared is 20x squared plus 30x over 4x plus 3 squared. And then I went the rest of the way down the rabbit hole and I pulled out the 10x, hoping that I would get something that canceled, but it never did. Yeah, so it never got any simpler than this.
Maybe move on past that then.
Right, so it never got any simpler than that, so I left it like that. Okay? So your homework today is just like combinations of those rules to find derivatives. And yes?
Do you ever want us to actually complete it out, or are you fine with just?
Like, go farther than this?
Yeah.
No, the only reason that you would want to is if, well, depending on what you were doing, like if it was really ugly and you still needed to put in an x value to find the actual slope, you might want to simplify a little bit farther. Or if you're checking the answer in the back of the book, and the answer in the back of the book looks like this, then you might, don't assume that you're wrong, just check to make sure you've simplified. Okay? And then on a test, I would tell you, like, completely simplify the derivative, okay? So your homework is gonna be page 263, 107 to 117 odds, of course, and then look at 123, 125, and 137. I think I chose a couple of those that actually ask you to find the slope at a specific point. So you'll have to put your point back into your derivative, or your x value into your derivative. Okay? Cool. Yay for you guys.